Hey, what is up? It is Saturday, May 28th, 2022, 10:25 a.m. At least my time it is. If you're in Australia or somewhere else besides the US, which you could possibly be, and maybe you likely are, yeah, then it's whatever time you know on your clock it is. Okay, anyway. All right. So, welcome to Coding with Shaft. Oh no, Shaft the Algo Guide. That's my actual name, my actual channel's name. And I am ready to do another coding problem for you. It is a nice, kind of overcast Saturday. And yeah, and I am just like trying every morning to get something going. And today I'm doing a medium problem on Leetcode. So before I continue, like, subscribe, and comment in the comment section if you like my videos. I appreciate any feedback. I know there's a ton of algo videos out there, but I hope I'm kind of help helping to explain how specific algorithms work as I increase my knowledge and hopefully share some of that and help increase yours. Okay, so with that being said, let's get on to this medium Leetcode problem. 208, implement trie, prefix trie. It's one of the blind 75. Okay, or I think it's a blind 75 problem. Either way, it's one of those problems that I'm trying to get through, and like really master my skills in all things data structures. All right. So a trie, or a prefix tree, is a data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications for this data structure, such as autocomplete and spell checker. And if you've done any amount of algorithm research, you probably know that already. Implement the trie class. Trie initializes the object. Insert, so the insert operation inserts the string word into the trie. Search returns true if the word is in the trie, and starts with returns true if previously inserted trie word has the prefix, and false otherwise. Okay, so look, if you've never seen how this works before, a trie is a pretty common and very important data structure actually, and especially in string matching, and it's used like all over the place, and it's a very practical data structure, which is why companies like Google love to use tries in what they do. I mean, it's paramount to their searching business, and it's paramount in genetics and bioinformatics. It's just all over the place, and so it's good to get familiar with the operations in plain English. So if looking at a trie would help, I think that would make the most sense, right? So, and there's different kinds of tries out there, but here's a simple prefix trie, right? And basically, you can think of it as organizing a bunch of organizing characters, and organizing words. Given a list of words, organizing the characters in a way that makes it easy to search for words by connecting words that have similar roots. Okay, so right, because take a look at this. This is a good example. So this is obviously some genetic information, and let's say these are prefixes. These are words that I've installed, or these are strings that have been inserted into the trie. The ACGT, this is not a bio class, but ACGT, or the bases, the genetic bases which make up the DNA, and nitrogenous bases, and we can use this trie to kind of store this efficiently, so we could search for these later, and we could search for fragments of these quickly later. And you might ask, well, why don't we just store all the strings together? Well, storing the strings and then searching them is something that's done as well. But a lot of the reason for a trie is because the connections between similar rooted words reduces redundancy in storage, and thus it makes storage and retrieval much more efficient. And that's why it's called a trie, because the TRIE part is retrieval tree. Retrieval, whatever, right? So that's why it's called a trie. So basically, I don't have to store AAAA separate from ACGT. I can store AAAA and ACGT and connect them together, and then if I want to search for them, I can simply go down this trie, traverse it using a standard tree traversal. And if you can imagine that in this specific example, it doesn't look like it saves too much time, but just imagine if I had a huge matrix of words, I would have a massive list of words that I can just fit into this trie format. It makes, again, computer science, a large part of it is about reducing redundancy and trading storage space and making more efficient structures for searching things. So that's essentially what's going on here. So if I had like a massive trie, you'd see the difference really. And here's another example, right? Because this trie, down nested here, all the way down here. By the time I get here, I see I can have the two words stored as for this one root rather than, and this is like an entire word here, and this is an entire word struct and string. I can have these two things stored rather than, rather than store them individually in a list. Okay, so now that I've gone through the basics of the trie, let's go and try to try to code this up. Okay, so first thing we do, a trie, in a tree, you can represent a tree as just a tree node and standard tree, binary search tree, etc., with a left and right child. In this case, we have like a enclosing data structure called a trie, and I want to actually create a concept known as a trie node separate from the trie. I'll explain how that looks in a second, but every trie, let's just say, has a root, okay? And now I'm going to write this trie node like this, okay? Or initialize this trie with a trie node of with this character asterisk as the parameter. So this character that I'm passing in is the character that's associated with each of the letters, and I use the star here because it's assumed right now that the trie can only contain alphanumeric characters, and that will keep this root safely out of only there for the structure of the trie, but not necessarily participating in the search. Okay, so now we have to look at what the trie class looks like. So if I have the trie node here, now design of the trie node is important because the trie node, so what is the trie node going to have? The trie node is going to consist of its own character, and it's also going to consist of children of the trie node. So here, let's say we're at A, then this has 2 children. If we're at the root has 4 children, A, C, G, T, right? And then the child is organized based on the letter of the first letter of the word that is inserted in the trie, and then the second letter of that word, its third letter, so on and so forth. Okay. So next thing I'm going to do, so the children is going to be, it could be an arbitrarily long list of children, and I made it a hash map because I want to be able to pick out children real quickly based on their character. Okay, so that's what the hash map lets us do. Otherwise we would have a list and then it would be slower. And then is word false. So basically in a trie, right, I can have ACG, but is ACG a word in the trie? No, because ACG was never inserted into the trie on its own. ACGT was, and therefore the word ends at T. Okay, so there's ways to, like, you don't necessarily need that variable. I mean, I kind of like that in this case, but in some cases it's a good idea to have it because let's say AC was inserted into the tree at some point. Well, AC is already encompassed by this path, so if I just put AC in there, I wouldn't know that it's a whole entity on its own, right? Unless I somehow marked C as the end of a word, right? So if I wanted to search for the word AC, it would be there. If I wanted to search for the prefix AC and I didn't have a Boolean variable that said if it's a word or not, I could do that. But if I didn't have a Boolean variable saying it's a word, and I wanted to search for whether the word AC is in the tree, then that's different, and you won't be able to do that without marking it somehow. So that's the point of that variable here. So public try node car C, and searching for prefixes and words is related, so you'll see how I relate those two. So basically, in order to insert a word, I'm going to create a helper function called insert. I already have a function called insert, so I'm going to overload it and create a helper function. This helper function, remember what I said I wanted to do. I wanted to iterate recursively through one of the branches of the tree, and I'm not doing any, I'm essentially going to write this in a way that I'm going to commit to a branch that exists already, and I'm going to insert downwards. So if index equals word length node dot is word equals true, return. Okay. Now, basically I'm saying is if I'm at the end of the word, this index is going to start at 0, and I'm going to iterate through the indexes, and you'll see where I do that. And when I get to the end, the base case of this recursion is that I'm hitting the word length, and if I'm setting that last node that I've traversed through to true, because as I said in my previous example, I need to mark it to let the try know that there is a word and not just a prefix stored in the tree. And it is called a prefix tree, but again, sometimes we want to know whether a whole word is stored there. So now I'm getting the character associated with the index at the current input string at its specific index contains key C. Okay. Now if the node is not in the children, this is what I was saying before, this is where we have to put the node in the child. Okay, we have to make it a child. We have to put the current character in there, because remember, we're adding to the try, right? So we add, and then once we do that, in order to go to the next level of the try, if we've already found the child, then we don't have to do anything. But if we haven't, then now we created the child, and then we can insert into the list, the child's list of children. Okay, so basically I'm recursively inserting. Does A exist? Yeah, no. Let's say A, this is a blank try. A exists. A, no. Then I put A. Then if I have A, then if A exists, which it does now, then I go down the list, and I'm like, oh, does the child A exist? Yes. No. And then I add A, and if does the child A exist? Add A. If the child A exists, add A. Right? And then in this case, if the child A exists, then we go to the next letter, C, and then so C doesn't exist as a child of A. Let's imagine this was in here. Then we add it to A, then G to C, and then P. So that's how we connect things together. We add, and if they already exist, we add to the child. Okay, that's important to really get. Now, searching. So searching for a word, let's do starts with first, because that's easier. We want to know if the try starts with a particular sequence of characters. Okay. And then if it doesn't, okay, so now I'm going to use this, I'm going to return this, create another helper function. It's prefix, okay, and this one I'm going to write, for variety's sake, a little differently. I could have written, I'm going to write this iteratively, and so how I'm going to do that? Well, how do you do an iteration through a tree? And this is not absolute, there's many ways to do this, but let's just get some practice using stacks. It's always good to vary your data structures a bit. So let's say I have a stack, and as you do searching using a stack, which is paramount to depth for search, which is essentially what we're doing for the most part, we're traversing depth. So index equals 0. So what am I doing here? I'm creating a stack so I can push roots onto the stack, and this is the recursion stack, the equivalent of the recursion stack, and I will go through the children. Again, now I don't need to do it like this, but I just wanted to get some practice using stack. So now here's the kicker. If stack is empty, and index is less than prefix. So these are the conditions. So while these conditions aren't true, while the stack is not empty, and while the prefix index is less than prefix dot length, I'm going to keep adding nodes to the stack. Now again, knowing how to do this is something that takes some practice from doing iterative depth first searching. But that's essentially what I'm doing. Are at index. Okay, so basically if the stack isn't empty and if the index is less than the length of the prefix, these are the two conditions which we're continuing to go adding letters through our iteration process. Okay, so now if node.children contains key, and I say contains key because this is the way that we traverse this string. We check the children to see if they exist or not, and if they do, then to the stack we add the next child that was found. And again, this is searching. We're not adding into the tree anything new here, right? It may be some advanced versions of this. You can do this simultaneous searching and adding, but for this purpose, we're just doing it this way. Okay, if children contains key, then we add the child and then we increment the index because that's the next character. Now, if we get to the point that the stack is empty, at this point, okay, then it better be because we are at a point where the prefix length is at the very end of the tree. If not, that means that right there and there, we return, this condition is going to return null, which will return false to the asker, right? This starts with. Because at this point, that means the stack shouldn't be empty, because if the stack is empty, without us being at the very end of the trie, because if the stack is empty, then that means that there's no matching character and therefore no prefix or word that we found, okay? Now, at the very end, let's say we get through the entire iteration above, then all we do, we're going to return the last element on the stack, okay? Now, how does this work? Okay, the last element on the stack, why are we doing this? We could just return true or false for is prefix, but I'm doing this on purpose because, remember, sorting and searching are similar. So not sorting and searching. Searching and prefix finding, searching for an entire word and prefix finding is similar because a word is going to be a prefix, but it's also additionally, so if it's not null, that means we've hit the prefix. This is our substitute for is true for the prefix, and now that's why we marked is word, because if we find a node and if we find that it's not a word, then we know it was just a prefix, right? And therefore this is prefix is sufficient, right? As long as that node is there, then we know there's at least a prefix. But that prefix is not necessarily a word, and that's why we tag the word separately when we insert it into the tree, and searching will require the last node of that prefix to have that is word boolean true. Okay, let's try it. Accepted. There we go. Okay, not the fastest. There are faster ways of implementing tries out there, but I just wanted to get the code out there so you can kind of understand how it looks like. These are all O of n operations, sorting and searching, and it's much faster than storing a list of, not sorting, searching, and adding, and it's much faster than just storing a large list of strings and searching for prefixes in those. Okay, so that's it for now. I hope you enjoyed this long video. I did accompany you with an explanation of a trie, and yeah, have a good day. I'll see you around. Like, subscribe, and comment, and yeah, have a good